All right, so if you're the kind of person who wants the blueprints, not the glossy marketing brochure, this deep dive is, well, it's pretty much custom made for you.
The real schematic.
Exactly.
Yeah.
When you jump into a new technology stack, Haskell, Python, whatever, there's always that fundamental question.
What's the bedrock?
What is the absolute bedrock? What is that unseen foundation that everything else rests on? And we're not talking about the cool web frameworks. We're talking about the atoms of the ecosystem.
And, that need to understand the foundation is really the shortcut to true expertise. Every project starts with some kind of tool that bootstraps it.
Right.
And when that happens, you instantly inherit this whole set of assumptions and dependencies. Our source material today just cuts right through all that noise. It investigates a brand new Haskell project made with the Stack tool.
And for anyone new to Haskell, Stack is basically the standardized build and dependency manager for ghc, the compiler.
The Glasgow Haskell compiler, yeah.
So our mission today is really just to decode those initial core dependencies. The source author did something really simple to get this insight. They made a dummy project, called it XS2 ebook,
Right.
and immediately ran one command, stass dependencies, and that just strips away all the other noise and shows you the essential packages. We are decoding the minimum viable runtime.
It's like forensic archaeology for programmers. You're literally excavating this starting point.
Yeah.
When you ask the system, what do I actually depend on to exist? The answer is surprisingly concise.
Okay, let's unpack this. So when the author ran that command, what came out was a list of just 6 items. And I think we need to lay this list out precisely, including the versions.
We do, because they represent the concrete artifacts that really define this whole foundation. Let's walk through it.
All right. Number 1, and I think you'd agree this is arguably the most important one.
Oh, absolutely. The big one.
The big one. It's the massive package base, version 4.2.2.0.
Following that, we get ghc-bignum, version 1.3.
And then we get into names that sound a lot more like the engine room of the compiler itself. We've got ghc-internal, which is version 9.1003.0.
And paired with that is ghc-prim, version 0.12.0.
The fifth one is, it's totally unique. It's different from the others we've mentioned. It's DS, version 1.0.2.
And finally, you always get the application itself. So XS2 ebook, version 0.1.0.0.
6 elements. That's it.
Just 6. But contained within those names is a critical structural truth about the whole Haskell ecosystem, and it dictates where you, the application developer, should probably focus your energy.
And that structural truth is really the core insight of the source material. It introduces this massive philosophical and practical distinction. The Haskell world deliberately splits its core libraries.
It does. It splits them into components for GHC end users versus components for GHC developers.
And that distinction is crucial.
It really is.
Yeah.
If we connect this to the bigger picture, this split dictates who needs to worry about which component. The GHC end user, so that's you, the application writer, you're building a product, you should almost never need to look below a certain layer.
I kind of see it like a car, right?
Okay.
GOT end users, that's us. We're the drivers. We're just focused on the steering wheel, the road ahead.
Right, the user interface.
Yeah. But the GHC developers, they're the engineers. They're the ones down in the engine block maintaining the fuel injection system. If you see a problem on the dashboard, you handle it. But if you need to overhaul the motor, well, that's a different set of tools.
That's a perfect analogy. And in our list of 6 dependencies, only 2 are explicitly categorized for those drivers, for the GHC end users. And they should be the immediate focus for anyone starting out.
So let's start with the one we already called the workhorse base, version 4.280.2.0. When you hear standard library in Haskell, this is what everyone means, right?
Absolutely. Base provides all the high-level core data structures, common operations. This is where you find the definitions for fundamental types like lists, tuples.
The day-to-day stuff?
All of it. Core I/O, utility functions, the basic arithmetic type classes. If you spend 90% of your time writing application logic, you're spending 90% of your time using base.
It's the abstraction layer that makes a language so productive. But that brings us to the second user-facing dependency, and this is where it gets interesting. ghc-bignum.
Right. It's listed as an end-user library, which is a bit strange because the name suggests something really deep and mathematical.
Yeah, ghc something.
And it is. It provides the low-level implementation for natural and integer numbers, specifically those really big numbers that, exceed the fixed size of a 32 or 64-bit integer on your machine.
Okay, but wait. If ghc-bignum is handling the low-level math, the actual machinery, why isn't it considered part of the compiler stack like the other ghc things we're about to talk about? Why should I, the application writer, care where my integer implementation lives?
That's a fantastic question, and it really highlights Haskell's commitment to mathematical precision. In a lot of other languages, if you need arbitrarily large integers...
Like a big int library or something.
Exactly, a big int or big number library. You have to explicitly go out and import it. It's an add-on.
So it's not just handling simple integers, it's handling arbitrary precision integers.
Precisely. And Haskell considers this so fundamental to writing correct, mathematically sound code that it includes that machinery, ghc-bignum, right in the core user stack. It's basically saying we provide robust, mathematically complete integer support by default.
I see.
So while base gives you the interface to the integer type, ghc-bignum provides the power to make that integer handle numbers into the quadrillions without overflow errors. It's an essential feature of the language, not just a compiler detail.
That makes perfect sense. It's an implementation detail that directly impacts the correctness of my application, so it has to be categorized for me, the user.
It does. And these two, base and ghc-bignum, are the primary focus for any application developer. Now, we can pivot to the other side of the fence.
To the engineers.
To the engineers, the components aimed at ghc developers. These are the foundational elements supporting the compiler itself.
These are the ones where if you start browsing the documentation, you might feel like you need an advanced degree in computer architecture. We have ghc-internal and ghc-prim.
Let's start with ghc-internal version 9.1003.0.
Right.
This is, it's the shadow library. If base is the public API, your steering wheel and pedals ghc-internal is the detailed schematic of the engine block. It holds the low-level implementation.
So when I call a function in base, that function is probably relying on code inside ghc-internal to actually do the work.
Almost always. It provides the essential glue and mechanisms that power base. ghc developers use it when they need maximum control or when they're debugging performance, but application writers are strongly discouraged from touching it.
Why is that?
Because the compiler authors reserve the right to change ghc-internal without any notice. It's an unstable API by design. It's for internal use only.
That's actually a fascinating insight into library design. You create this private, unstable implementation layer, ghc-internal, to support a clean, stable public layer base.
Exactly. It guarantees that if the compiler team wants to drastically optimize how, say, lists work, they can change ghc-internal without breaking every user's code, as long as the base API stays the same.
Stability for us, innovation for them.
Precisely. And if ghc-internal is the schematic, then ghc-prim goes even deeper. This is version 0.12.0.
So if we stick with the car analogy, if internal is the engine schematic, prim must be like the raw elements, right? Like iron, ore, and rubber.
That is an excellent way to put it.
Yeah.
ghc-prim deals with low-level primitive types and operations. These are things that map directly to machine concepts, raw pointers, unboxed data types, fundamental memory operations.
Wow.
If you are working at this level, you aren't writing a Haskell application anymore. You're writing code to build the Haskell compiler.
Here's where it gets really interesting, because that moves us to the one component that operates completely outside this library model. certs, the runtime system.
The runtime system, or certs, is unique. It's the critical core that provides the operating system layer for your compiled Haskell program. Unlike every other library we've talked about, which provides code for specific functions or data, certs handles core dynamic tasks that have to run constantly in the background.
And what kind of tasks are we talking about here?
Everything you take for granted in a modern language: memory management, garbage collection, scheduling. When your Haskell program runs, it's not just running code, it's running within the dirt's environment.
So it's handling things like parallel execution and threads.
All of it. It makes sure Haskell's concurrency features are handled efficiently.
So it sounds less like a library and more like a crucial intermediary between my compiled code and the actual host operating system. It's the OS for the Haskell app.
That's the most accurate way to describe it.
Yeah.
And the source material highlights this really unique detail about it. Certs cannot be found on Hackage.
Hackage being the central package repository for Haskell?
The central repository for the entire community, yes.
And why is that detail so crucial?
Because every other dependency we listed, base, ghc-bignum, all of them, you can technically browse them, download them, install them via Hackage. But because the runtime system is so intimately tied to the ghc compiler's very existence,
It's not optional.
It's not optional. It's not treated as a separate library. It's bundled with GHC. If you have the compiler, you have the art. You can't just install a different version of the runtime independent of your compiler. It emphasizes that this component is utterly non-negotiable for the machine to even function.
You know, reflecting on this whole stack, we have the machine primitives in ghc-prim, the implementation in ghc-internal,
Mhm.
the operating core instarets. It's amazing how this powerful low-level foundation is basically invisible to me as an application developer, unless something goes very wrong.
Mhm.
But it's what enables the elegant, high-level stuff in base that we use every day. It's the ultimate demonstration of layered abstraction.
And that abstraction leads directly to the core practical advice from the source material. It basically gives you permission to ignore complexity.
So what does this all mean for the learner? If I'm that developer trying to build my app, where should I be studying? Do I need to memorize the nuances of sort scheduling?
The source material gives a very clear and, I think, liberating directive. Unless you plan to dive into the compiler's internals, or contribute to GHC, or do some highly specialized system programming, focusing your energy on mastering the base library should be adequate.
That is an incredibly efficient use of study time. It shrinks the universe of what you need to know from 5 system-level components down to one primary focus for productivity.
It's about knowing your data structures, your I/O functions, your utility functions, and that is almost entirely contained within Base.
It just gives you a clear path forward.
It does. If you're building an application, dedicate yourself to understanding the idioms and abstractions the Base offers. You can trust that the compiler developers have managed the complexity of ghc-internal, ghc-prim, and aired, so you don't have to. It's permission to stay focused on solving the business problem.
Not the computer science problem.
It's not the computer science problem.
So, to summarize the major points of this deep dive, you bootstrap a new Haskell project with Stack. You get a foundation of 6 key components. These are clearly split into tools for the end user, Base, and ghc-bignum,
The stable application layer.
and the highly specialized tools for the GHC developer, ghc-internal, ghc-prim, and the integral certs. You now have the foundational map. You understand the boundaries.
And that foundational knowledge is a definition of being a well-informed developer.
So what does this all mean? It means abstraction works, but knowing the layers underneath makes you a much more confident developer.
And building on that idea of layers and boundaries, let's leave you with a provocative thought to mull over. We've established that the standard application developer lives in Base. But what specific kind of scenario, what extreme constraint or performance need or system integration challenge would require an application developer to intentionally cross that boundary?
To go deeper.
To go deeper, why would you ever feel compelled to bypass the stable, high-level Base interface and interact directly with a developer-facing library like ghc-internal or, even more dangerously, ghc-prim? Consider the niche applications, maybe interfacing directly with custom hardware or writing extremely tight cryptographic loops or interacting with C code that might force a user to intentionally step outside the comfortable abstractions and manually deal with machine primitives.
That's the territory that separates high-level development from advanced system programming. Something to ponder until our next deep dive. Thanks for joining us.